Welcome to the world of geometrifying trigonometry. You already know that there are the several kinds of trigonometry where hyperbolic trigonometry, elliptical trigonometry, and rational trigonometry is also there. Uh, when we are talking about geometrifying trigonometry, our fundamental mission is to convert any trigonometry expression into the geometric figures like Euclidean geometry figures, as we used to do in school days to prove things with the ruler compass, to construct the geometry with ruler compass. We are trying to implement those kind of mechanisms here, and this picture you can get in Google. If you search with geometrifying trigonometry, you will get this picture and operators understanding. Whenever we uh, focus to make any new algebra, like Hamilton, Professor Hamilton tried to prepare quaternion, the four-dimensional number system, and complex number. It is also a new kind of algebra. It is extending the real numbers to higher domain. Then vectors came, and the world is changing. After that, the higher dimensions came. But this is another different kind of algebra where plus, minus, into, divide are well defined, but we cannot say these are behaving like fields. These are not always behaving like fields. If we work with trigonometry, pure classical trigonometry, then plus, minus, into, divide works, because in that case we use pure numbers, real numbers, that is rational or irrational, and numbers are fields. Plus, minus, into, divide all works. In geometrifying trigonometry, plus works in two different ways. In the previous video we have already shown that minus works in two different ways, and four symmetry are always common for every operators. For multiplication also there are four symmetries for every six different ratios of trigonometry: cos, sine, tan, sec, cosec, cot, and six types of ratios, and for which there are four types of symmetry for each of these things. Geometrifying trigonometry extends trigonometry to another level where we don't fix ourselves, we don't keep ourselves bounded only within right angle triangle. We will generalize it to any kind of triangle: isosceles triangles, scalene triangles, or equilateral triangle, whatever kind of triangle we can take, but we can do trigonometry on that. So we have changed some conventions here. Like in hyperbolic geometry we used to make the terminology like cos h theta, sin h theta, in that way. Here we will extend it to cos gt theta, sin gt theta, tan gt theta, in that way. That is a future thing, and we will demonstrate those things in later videos. And it will take time to come up with those videos, because that is advanced geometrifying trigonometry. We can tell it as a generalized geometrifying trigonometry. Currently in this video we will explain the basic things of multiplication, and in this picture you can see for the right angle triangle, if we confine ourselves in this discussion only with the right angle triangle for some minutes. For a right angle triangle there is a seed angle, which is the smallest angle in the triangle, and which angle is present between hypotenuse and base. For right angle triangle, one angle is 90 degree, which is the biggest angle. The smallest angle is the pivot angle, which is the controller angle, and it is seed angle, and that angle is formed at the point pivot. The point where 90 degree is formed is called the stretch angle, stretch point, and the point where the 90 minus theta is formed, 90 minus seed angle is formed, that is the nodal point. The 3 points are important in geometrifying trigonometry. Please try to think those days when Pythagoras was defining the theorem, perpendicular, hypotenuse and base, the three names were defined first. Until these three names were defined, we could not say p square plus b square is equal to h square. We could not say the thing in that way. In geometrifying trigonometry, there are several theorems which are involving the points, not only the lines. The points are also coming up with several interesting theorems, and line segments are also having different names. But since we are trying to generalize the theory to any kind of triangle, so we will consider the largest angle forming in any triangle is the stretch angle. Smallest angle forming in any triangle is the pivot angle, and the other point is nodal angle. Similarly, the point where the smallest angle is forming is pivot point. The point where the largest angle is forming in any triangle is the stretch point, and the point where the other thing, that is the medium angle is there, or it can be equal to any other angle, but it is a nodal point. In that way, we will consider in GT perpendicular. For the geometrifying trigonometry terminology, the perpendicular is the opposite side of the smallest angle. Hypotenuse, GT hypotenuse, will be the opposite side of the largest angle in whatever the triangle, and the base is the opposite side of the other angle, that is the nodal point, the opposite to the nodal point or the nodal angle, then that is the base. Up to this, the concept is told here. Now, how the multiplication is done? For the multiplication concept, we are confining our thoughts into the normal trigonometry. In the classical trigonometry, suppose the right angle triangle is there, and if we want to multiply cos theta with a sin theta, how? That means the sin theta cos theta. If we try to say sin theta cos theta, then first the hypotenuse is taken as the L, that is the given line segment. Take its perpendicular and align the copy of this triangle. Take the copy of this original triangle. This initial triangle is the seed triangle. Make some copies, and if we take the copy of the seed triangle and carry the hypotenuse, align and scale to fit to the perpendicular of the previous triangle, then this point goes here, this point goes here, and it's stretched also. In the CAD, in engineering world, this command is called the align and scale to fit. This is aligned and also scaled to fit. The hypotenuse is scaled to fit to the perpendicular. Then we will get sin theta into another triangle is coming there. Then we can find these kind of pictures and we will construct these kind of things. And there are several theories in Google that you can find. In GitHub also you will find those theories, and in automated trigonometry simulator you can check these things. Now I will show you by constructing hands-on in front of you. This is the way we do the multiplication. And multiplication, the reverse process of multiplication is division. We will also discuss on those things on the later on videos, and that will give you more clarity. Now coming to GeoGebra, obviously we'll get the link of this file in the description of the video. You can play on that and you can get more understanding with that. Suppose how to make a seed triangle. Very easy. Take 3 line segments. This is one line segment, this is another line segment, and this is another line segment. Now when 3 line segments are prepared, now we can see that GeoGebra auto locks the points, and now the triangle is ready. Whatever the triangle is there, the triangle is ready. Now if we consider this as a seed triangle, if we consider this is saving at that online location, if this seed triangle is ready, now we can take it as a seed triangle, or we can generalize the geometrifying trigonometry to the generalized geometrifying polygonology or polygonometry. But now we are focusing on triangles only. Let's define this as the polygon, and this is the seed triangle, and we can take it as a seed triangle, the reference triangle with which we will play our game. Now this is reference triangle, and we will not touch it every time. We will take the dimensions from it to do every work here. How can we achieve this? Now in CAD or in any engineering software, there are options for blocks, but here the block option is not present. But it is not good also to design new algebra. For algebraic purpose, we have to define everything with the construction protocols and algebraic methodologies. Suppose this is a seed triangle, and we have duplicated it with Ctrl C, Ctrl V. Now this is a seed triangle, is copied. This is taken as the first triangle on which we will work. Now we have to decide which one is the given line segment. As per the given expression, if the expression is saying that it is hypotenuse, then it is hypotenuse, and it is a bad practice to copy it, because it is not allowed in mathematical terminology. This is the, for engineers it is okay, but for mathematical thinking it is not a good habit to copy the reference. We should make the things with the construction protocols. Every time you have to prepare things with construction protocol. Now suppose I have to make a line which is equal to this hypotenuse. Suppose we have to do cos square theta, cos theta into sin theta. Suppose this is a right angle triangle. Suppose we have made our sense in that way, it is a right angle triangle. Now to make a cos square theta, first of all we have to consider that the cos theta means base by hypotenuse. The denominator of the ratio is the input, and the numerator is the output of the first ratio. So denominator is input, so we have to take the denominator, the hypotenuse, as the initial line segment. Since it is the initial line segment, so we will make it L. How? Here we come and we will define it as the initial line segment L, caps L, that is as per geometry trigonometry convention, it is taken as L. This is taken as the B, and this is taken as the H. Say this is taken as H. Now we will reconstruct this mathematically in Euclideanly. We should say it as Euclideanly. We will take compass, we will take any center point here, or you can take any point where we want to put the construction. Now it is taken as the center and circle. This is a circle taken whose initial line is here. That is, first we will draw the L and place it here. This is the hypotenuse. Then we will take a line segment from the start to the circumference. It is the hypotenuse. Now we can change its direction here. Now if we make the circle with this as a center and this as a radius, we are simply copying this we are simply copying this system and we are drawing another circle with the compass where the end point is centered is here, radius is this, and placing it here. Now we have to find the point of intersection of these two circles, and if this is made, then we can copy the exact seed triangle here, and this is the way we construct the seed triangle and saving it. Now the seed triangle is formed, and this is the art of generating the seed triangle copying. Now we will make these circles almost hidden. We'll make these almost hidden such that this will not disturb us while working. This will help us understanding the reconstruction of geometry. I think school students will also feel happy because they will see construction of geometry from trigonometry hands-on. When they will see these videos, they will get the ready reference of how to construct geometry and how engineers do these kind of things when parametric calculations when they need. Here's the magic. If you drag these points, you see that the references are locked. Now the follower triangles, this is the master slave relationship. If we change the seed triangle, then the reference triangle will also change accordingly. Now this is the copy of that L, means this is the L1, we can say L1, and this is the copy of B, so it is the B1, and this is B1, and this is H1, this is H1. Now if this is H1, then we can say that if this one is L1, then this one is the L1 cos theta, and if the angle here is theta, if angle here is theta, then angle here is also theta. And how can we check that? We can see that both angles are having same value, and we can give it a caption, and we can give it a caption here, which is suppose here alt 233. Interesting thing is GeoGebra supports these Greek names equal to caption. This here we can show caption and value, and here it is showing caption and value, and we can show it like this, and here also we can set it as a caption, and also caption and value, so it will show here also the same value. So we can cross verify. If we change the sides, the same value are reflected in the copy, because as per the construction protocols the seed angle is copied here. Now we will do the same thing here with the more intelligent way. Now this one is the first copy. Now we will do the multiplication. And how can we do the multiplication here? We have to draw this as the hypotenuse and the same copy of the angle here or here or here or on from this side. So 4 symmetries are possible. We are taking one symmetry here such that we can show at least how the multiplication construction is worked. Now we will take this as the first hypotenuse and this as the second hypotenuse. In the caption we can say this one is equal to h1 is equal to L2 because that is the hypotenuse. This one is the h1 and that is a perpendicular. I should write it as perpendicular because this one BC and this one is H. No, I should write it differently. This one is H, or that is height, but here base and perpendicular, writing it as the perpendicular is a good habit to write it, then it will not disturb us. Here it is not H1, I should write it as P1. This is P1 and this P1 is now becoming P1 is now referring to hypotenuse of second triangle. This P1 is referring to the hypotenuse of second triangle. So we have to draw the similar triangle of the same seed triangle such that this side should be equal here. How can we draw that? We can take a complete line here. And we can make it shadowy, and we can set it shadowy here, and its style is taken lighter such that we can get the reference, because first we will do the aligning, then we will do the scale to fit. First let us do the aligning. How can we do the aligning? We can draw the circle here with the center of this size, this point, and size of the radius is like this, placing that at this center, and then we will get the point of intersection. We will get point of intersection between this and this, so we will get the aligned hypotenuse here. That is very important task to do, because P is turned into hypotenuse. Now first we are doing the alignment, then we will do the scaling. So first thing first, we are doing the alignments, and then we will think of the scaling. If necessary, we will do separate video for that, but alignment is done first, and we should place its color as a different, so that we can identify that this is the aligned hypotenuse. Now when this is aligned hypotenuse, we have to copy this line here, because this is the base here. Now again we will take the compass here with center here, and this one as the radius reference, putting the center here. And now where will that cut? This will cut at the another circle which will have this side and end point as the center. We will draw that compass circle where its end point is here and radius is here and it's placed here. So we have found that third point of the copied aligned triangle, and this is the third point, and we can draw the line here which is aligned and not yet scaled to fit, but aligned at least. Now we have got these points. These are the mechanisms of drawing Euclidean geometry from the conceptual model of geometrifying trigonometry, referencing the art of doing multiplication as the definition of align and scale to fit. We are doing that following the rules of geometrifying trigonometry. As per the definition of geometrifying trigonometry, we are doing multiplication through the Euclidean way, and this is the formulation which we learn in engineering drawing. And Professor Cremona and 1860 in graphical statics, he mentioned this concept. And interestingly, this is the generalized trigonometry, where you can see that if we change the things, then aligned triangles are also changing, and this is the art of geometrifying trigonometry. Now we have to scale to fit. How can we do the scale to fit? This alignment is done. Now it's very easy to do the scale to fit, because we can draw a parallel line of this line. We can draw a parallel line of this line through this point. How? Here we are drawing the parallel line of this line, putting it here, getting the point of intersection between this and this. Now we have found the output triangle. So that we can understand that this one is the align and scale to fit output of our final triangle, and this one is the initial triangle, which is a copy of the seed triangle, and we can control everything with the seed triangle. And geometrically referred, we have done everything geometrically referred, so it is easy for us to handle all the things through seed triangle. Now you can see that this is the way we do the align and scale to fit. Irrespective of the angles and the types of the triangles, it will do the multiplication and alignments of our whole thing. So we have understood how the multiplication is done in geometrifying trigonometry. Irrespective of the type of triangle, it still works, because the convention of multiplication is common, and it will work every time, whatever kind of triangle it is. Even it is not right angle triangle, still the convention will work. Thank you. We will proceed with more detailed, deeper understanding later on. With the automated trigonometry simulator, you will get already these outputs when you will put the data, such that we can do more experiments, more deeper experiments on these. Every time it is laborious to do these kind of constructions, so we have made that simulator such that all these circle constructions is not necessary. It will automatically generate the outputs such that you can visualize the things very easily. Thank you.